left, if a small amount is epsilon, as it often is, small positive amount is epsilon, then what is that actually? If that distance is epsilon, what's the name of that point that's our new upper bound? S minus epsilon. Okay, so what is this telling me? This is telling me that this thing is the soup provided if I go to the left. So if I look at S minus epsilon, what has to happen? What has to be in there? It can't be lacking in things in A. But what's that actually saying?
It has S minus.
There has to be some A in there. So you can't have all the A's pushed to the left, okay? Okay, so let me now often, and this is the way you should think of these sort of epsilons that come up in analysis and calculus. You can think of them as getting smaller and smaller, right, or being arbitrarily small. Okay, so let me just draw my new picture, okay? And what this says, if this is my S, it's going to be the soup provided if I move to the left a little bit, there's got to be something in A. If I make it even smaller, there's still got to be something in A. If I make it even smaller, there's still got to be something in A. And so the way you think about this is that if you have the soup as opposed to just some other upper bound, right? So we've got that it's an upper bound. We got that, right? Okay? But if it happens to be the soup, no matter how close you squeeze up against it from the left, there's got to be something in A in there. A doesn't have to be an interval, right? So A could just be a sequence, for example. Remember those from calculus, right? But somehow the points in A have to be pushing up against that, getting arbitrarily close. Okay? That's what separates it from just an ordinary old upper bound, which is out here somewhere. So you always stop at the soup, and you never get close to that one, right? The soup is the only one that you get closer and closer and closer to. Now this should explain to you why I said before the completeness axiom tells you that if you have a sequence that ought to be converging according to some of the laws you learned in, rules you learned in calculus, that the completeness axiom gives you that it actually does converge to something, that there's no hole there. Okay, so at least here, if you think of an increasing sequence, which is bounded above, remember you had a test for that, right? If you took that level of calculus yet, right? That it's supposed to have a limit. Well, at least in that particular case, and you can actually get all the limits, and it's harder to explain what it means to should converge, right? Something called Cauchy sequence, which you learn about in analysis, okay? But basically, the completeness axiom not only gets you this sort of test for that there's a limit, but everything that should converge does. Okay? And so what I'm about to write down should remind you of the definition of a sequence converging to something. Okay? It should somehow remind you of that. Okay. So the second condition, A2, let's try to now formulate a statement, okay? So is this about some epsilon or is it about for all epsilon?
For all.
Yeah, because the statement is no matter how small you make it, okay? So that's a for all statement because all of them, small as you like, all right? So for every epsilon bigger than 0, there exists what? So here's the picture, right? Here's what we wrote, right? S minus epsilon. And so we must have some, which is a there exists statement. So there exists what?
A element of A greater than S minus epsilon.
Yes, LA and LA such that A is greater than S minus epsilon. Okay. So what we're going to prove in the remainder of class is that these two sets of conditions are equivalent. And we've already sort of seen the proof over here, right? You've sort of seen it. But what we're doing now, just like we translated this intuitive idea about getting closer and closer and closer into a statement about epsilons, and this is the standard way to sort of encode in mathematics getting closer and closer. For every epsilon, and then that epsilon is your closeness, right? And then there are all kinds of things you can finish with that, right? Like you can use the definition of continuity, you can use differentiability, all these things that you learned about can be, you use these epsilons as a notion of closeness. Okay, so, I don't know, I called it a lemma. It seems a little too important for that, so I'm going to call it a theorem in here, right? Okay, so let A be non-empty, and again, A is a subset of the real numbers now. That's going to be true from now on unless I, say otherwise. Oh, and bounded above. Then S equals sup A if and only if A1 and A2 are true. Okay, so this says you can completely replace S1 and S2 by A1 and A2 if it's suitable for you to do that. And in many cases it is. In many cases it's much easier to use A1 and A2 than S1 and S2. And again, the reason for that is that when you're dealing with an arbitrary upper bound trying to do A2, that's up here somewhere and it doesn't really have any good connection to A. Whereas if you're trying to use A2, there's a very clear connection to the set A, right? You have to find this element in there. Okay, and this becomes like those exercises that you did in calculus. Given epsilon, can you find the A and element of A with this property? And we'll do some concrete examples next time. Okay, so all right, so okay, so this is an if and only if statement, so we have two directions, right? So for this direction, we're going to suppose S1 and S2, because those are the two conditions that make S the sup of A. Well, since one's easy, right? Since S1 and A1 are the same, we need only show A2. Okay, and our picture right here is going to be very useful for the proof. And again, you should think about this because this is what you have to do as you get farther in mathematics. You have to be able to take your idea for how to prove something and write it down. Everybody agree? We just have to show A2 at this point. Okay, well, A2 is a for all statement. So what should our opening line be?
Are we doing contradiction or not?
Well, we are. But if you were just thinking about this directly, what would be your opening line? Well, this is a statement about every epsilon. You're showing about every epsilon, right?
There's just an epsilon greater than 0.
Well, let epsilon be bigger than 0. Okay. But somebody's already suggested maybe it's better to do this by contradiction. And so let's go back to our picture and see why that might be true. Okay? So remember how we got here. We said, well, let's suppose we shifted to the left and there was nothing in there. What does that make S minus epsilon?
An upper bound less.
It makes it an upper bound of A. And it's less than the sup because epsilon is bigger than 0, and that's our contradiction. Okay? So again, before you kind of jump in, and we're getting to the point where, and it's going to get more and more like this, where there's not just a follow your nose strategy like there was with set theory. Here's your opening line, write out what it means, write out what it means, right? And that was just to get you used to what a proof is, right? And now there may be different things to think about, and so before you try to write down a proof, you should go back and think about the idea that you had and try to translate that in. And the idea really here that we got was a proof by contradiction, right? That if there's nothing in there, then this is an upper bound and that's a contradiction. So now we need to write this down. Okay, so let's suppose not. Now, here's where all those painful exercises I gave you negating these crazy things should come in handy, right? So we have to negate A2. So what is that?
For some epsilon greater than 0.
Okay, for some, or there exists.
A is less than or equal to S minus epsilon for all A.
Yeah, it's probably better to, you know, we can put the for all anywhere, but it's got to be there. So you put it at the end. So we'll use your wording. That's fine, right? So A is less than or equal to S minus epsilon for all A, an element of A. Yes? But by definition, what does that make S minus epsilon? Yes. Right? A is less than or equal to this number. You can call it M in your mind if you want, but it's probably better for you to not. Just think of it as a quantity. A less than or equal to S minus epsilon for all A, an element of A. That's precisely what it means for this thing to be an upper bound. Right? And again, we're starting to do sort of reverse things here. Before, it was just, here I have this, what does it mean, right? And write out what the definition is. What you also have to be able to do is recognize when the definition is being satisfied. And say, oh, this is the definition of S minus epsilon being upper bound. So S minus epsilon is an upper bound of A. But since epsilon is bigger than 0, S minus epsilon is what?
Less than S.
Less than S. And that's a contradiction. What is it actually contradicting?
S is supposed to be less than or equal to all.
Otherwise known as S2. Right? Because this thing is an upper bound, but it's less than that supposed soup, and that's a contradiction to S2. Okay, so we've successfully translated that picture going in this direction into a proof. Okay, so let's go in this direction. So for this direction, we suppose A1 and A2. So as before, we only need to show S2. Okay, so taking a hint from what we did before, here's my A. What we know now is A2, so that means we have our S here. And so what we would want to do, if we were going to show this directly, is to show that if M is an upper bound of A, then S is less than or equal to M. Well, so let's negate that. To prove this by contradiction. Because if we negate that, then we're going to have an upper bound that sits where?
Less than A.
Yeah, we're going to have an upper bound that sits over here. And what does that tell you? That tells you all the elements of A are over to the left of it. But if they're all over here, what does it tell you about this little gap? There's no A's in there. So all I need to do is give this little gap a name, epsilon. And then M becomes S minus epsilon. Okay? So this one's a little easier to negate. Then there exists an upper bound M of A such that M is actually less than S. We need an epsilon. And remember, this is a for all statement, right? Since it's true for all epsilon, I can pick